My name is Enrico Bottazzi. I'm a researcher at PSC, which is a team inside the Ethereum Foundation. And today I'm going to present you Greco, which is a zero-knowledge proof for valid RLWE ciphertext. So the goal of my presentation is mainly twofold. The first goal is to making you understand what is Greco and especially why this is useful and how you as a potential application developer might benefit from that or might need like something similar to that. And the second goal is to explain what are like the main bottlenecks when you're trying to wrap FHE data structure, FHE operations inside the zk-SNARK, and share with you some of the tricks, the design tricks that we employed to achieve some, let's say, acceptable performance with Greco. And this is like the outline. So I'm gonna start with describing a very simple application to explain why we need something like Greco. So this is a secret voting application. When I say secret voting, I mean that the vote itself is secret. The tally is simply computed by summing up the ciphertext. So each ciphertext is encoding a vote, which is either 1 or 0. And we expect a valid ciphertext to be a form of encryption of 0 or encryption of 1. And of course, you know that when it comes to FHE, even if many people submit the same encrypted vote, encryption of 0, for example, the ciphertext will look always different. But this property is good from one side, but it's also bad to the other side because a malicious voter can send an invalid vote, an invalid ciphertext, which is encrypting this very large number that has nothing to do with like the valid votes. And if we add it up to the tally, this will kind of mess up the whole election. And by, let's say, from what it comes out of FHE, out of the box, there's no way to avoid that. So this is a problem that doesn't only apply to this secret voting application, but what I claim is that almost any FHE-based application will need to face this problem and will therefore need to require to check the correctness of the ciphertext that are submitted. And we'll get to the concept of correctness in a moment. But I also want to say that it's not always the case. Like there are also FHE applications in which something like Greco is not needed. And I think that these are the class of application in which the party that is performing the encryption is the only one that is affected by the result of the homomorphic computation done on this ciphertext. So an example is like the traditional private cloud computation. So you are the only one that really care about the output of this computation. So if you put like garbage in the encryption, you will get garbage. So it's really up to you. Or another one, it might be private information retrieval, in which you are the one submitting this bit vector of inputs. And if you put something malicious, well, it has only effect on you. So I would say that in that context, you wouldn't need any Greco-like construction. And when I say correctness, I mean two different things. So first thing is that a user must be able to prove that the ciphertext is a valid ring learning with error ciphertext. But this might be not enough because, like, for example, in the example that I mentioned before, if you encrypt like this very large number as a vote, yeah, you can still be generating a valid RLWE ciphertext, but it will be not correct according to the application requirement. So the second thing that we need also to prove is that the plain text message that has been encrypted is meeting certain properties. And we cannot separate the concern of these two type of proofs, which like the first one is more a general one, and this is what is addressed by Greco, by what I'm gonna present you today. And the second one is more like a complementary type of proof, which is specific to the application, which is more related to the business logic of the application, and might be, for example, like the message can be either 0 or 1, or the author, the voter must be one of this set of people. So you can be very, very creative on that and eventually wrap it up together with a proof from Greco to kind of make, let's say, increase the security of your FHE powered application. I'm gonna go through some background before getting specific with Greco. I think that most of the stuff here will be rather familiar to you, but I think it's also good for completeness to go through that. The first notion that we analyze is learning with error. So this is a very simple slide that, as you can see, what we see here is that we have like these matrices, then we multiply by this vector, and we have this other vector, we get this. And at the bottom, you see the formula here. But the important thing here is that this learning with error problem is at the basics of fully homomorphic encryption. And the real challenge here is that if you have at your disposal this matrix A and this vector B, it's very, very difficult for you to get this secret vector. And this is possible because we add this noise, and this is also possible because we're working in a, well, all the elements are integers modulo this 13 in this case. And there's also a variant, an extension, I would say, to learning with error, which is ring learning with errors. And the formula, as you can see here, is basically the same as before. The only difference is that now we are working with polynomials rather than with matrices and vectors. And the other difference here is that we have a specific definition of this polynomial. Let's say that this polynomial exists in this expression, which denotes a ring of polynomial. And what it basically means in a very informal way is that all the coefficients of this polynomial must be integers modulo this number. And also all the operations between polynomial are performed modulo this other denominator polynomial. And this is like this modulo operation between polynomial is really similar to what you do between integers. So you just divide your polynomial by this, and you take the remainder out of it, and this remainder will be a polynomial inside this ring. And you can tell that all the polynomials of degree less than, in this case, 4, of which coefficient are integers modulo 13, are included in this ring. We're gonna explain also a bit about BFE, which is the scheme that we're using to showcase Greco. BFE is a leveled scheme. When we say level, we mean that we need to know in advance what is the depth of our circuit, and we need to set the parameters accordingly. So we cannot just perform like operation forever compared to other scheme that supports like faster bootstrapping. And what we focus on here is only the encryption operation of PFE. So in this presentation, you won't hear anything but encryption. So all the other algorithms like addition, multiplication, decryption, I'm not really concerned with that with Greco. So this is the definition of encryption in the PFE scheme. And you can see that this is rather similar to what we saw before, but there's a difference. There's this K that appeared, and I'm gonna kind of explain that. So something also new in this notation is this Q, which is the ciphertext modulo of the polynomial ring. So the one that was 13 before, now we set it as Q. And this is the definition of the polynomial ring. And we also specify how we get this A, S, and E polynomial. A is a polynomial that is uniformly sampled from the ring. S is sampled from this distribution key, which is usually a distribution in which the coefficients are either -1, 0, or 1. And E, which is the error polynomial, is sampled from an error distribution, which is a Gaussian discrete distribution, truncated Gaussian discrete distribution. And K is actually the most important thing, because when we do encryption, we have like the secret, which is the secret key that we are using for encryption, but also there's a message that we want to encrypt. And if we were simply to, let's say that rather than K, we have M, which is the message polynomial. If we were to simply add M, we will end up in a situation in which the message is somehow mixed with the error. And this is bad because it wouldn't allow to recover the message during decryption. What we do instead is we multiply the message, which, by the way, is defined in this plain text modulus, which is much smaller than the ciphertext modulo. We multiply the message by this scaling factor Q divided by T, and this allows us somehow to move the message away from the error. When we say move away, it means like occupying more higher bits in the coefficient, while the error, we know that this is bounded in this error distribution and therefore occupy low order bits. And this is allowing us to somehow encode a message, encrypt a message in this ciphertext, which is defined by two components. Another notion that is important is the Chinese reminder theorem that you might have used in other contexts. And when we have like a large number, which is Q in our case, the ciphertext modulus, we can also define it as a product of factors Qi's, as long as these factors are pairwise co-prime. And using this technique, we can leverage, we can express any integer that is defined modulo Q as its CRT component. So it's like the X modulo each smaller QIs. And what we end up is that we have like many CRT components of these integers that are like smaller. So sometimes you don't want to deal with like big integers because your computer has a 64-bit compatible processor. So you want to perform like native arithmetic operation. And this is what is good about Chinese reminder theorem, because we can keep performing the operation on the CRT components, and just at the end, if we want to retrieve the representation in this in modulo Q, we can we can do that starting from the resulting components of this operation. And we introduced this CRT setting because we also want to perform BFV in this CRT setting, because we need to do BFV in a zk-SNARK, but we'll get to that later. And the main difference here is that, of course, like we now have like CTI, which each I is a different CRT decomposition of the ciphertext. And the nice thing is that all the operations that were before performed in the ring RQ can now be performed in the ring RQI. And there's also another property that is explained in this paper. Like you can see all the references in the actual Greco paper at the bottom. If we choose Q and T, so the ciphertext and the plaintext model, such that they are co-prime, we can calculate the K directly in the Chinese remainder theorem using this formula. So what we end up with is like splitting this K in two components, K0I, which is the negative of the multiplicative inverse of T modulo Qi, and this polynomial. And the good thing, like what we want to achieve by doing that, is that since you see like there are like some polynomials here that they don't have the notation with I, and this means that they are the same across each I decomposition of the ciphertext. And this is good because it means that we need to calculate them only one, we need to enforce some constraint on them only one, and we can then reuse them across each I decomposition. And also, as a side note, sometimes you also hear the term RNS, residual numeral system, I think. And this is, I think it can be used interchangeably with CRT as a term. And the last part in the background is the definition of zk-SNARK. Is an informal definition, and it defines as a proof. A zk-SNARK is a proof for a relation R in which we have a protocol between a prover and a verifier, and the prover wants to convince the verifier that for his witness and his instance, the relation is satisfied. And we usually have like these three main algorithms for a zk-SNARK protocol. And also, probably on a more colloquial level, you often hear witness being called as the private input and X or instance being called as the public input. So we'll stick with like this very colloquial definition throughout the presentation. So now we can get to Greco. As I said before, the goal here is to prove the validity of the formation of a ring learning with error ciphertext. And in specific, we are focusing on BFV, secret key encryption, and in this CRT setting. And we'll see why we really like this Chinese remainder theorem. But in general, you know that most of the schemes rely on ring learning with error, most of the FHE schemes. So I think that they differ from some encoding, some scaling, but in general, you can think that this can be also applied to other schemes. And I think it should also be applied to other schemes. So our task is to design a SNARK that is proving this relation. And if you were following before, like you see that the ciphertext actually has two components, CT0 and CT1, but CT1 is actually the negative of this A1, which is a public input of the ciphertext 0. So we don't really need to prove anything about CT1 we can just expose this A as a public instance of our zk-SNARK and let the verifier also check in addition that this is matching the second component, the CT1 component of the ciphertext. We're gonna go through like I don't know, like the idea is more like, okay, we present a challenge and then we explain how the challenge has been overcome in the Greco implementation. So the first challenge is really about like how to represent this value, this coefficient of this ring polynomials in our SNARK. Like our we have some limitation on the witness value, which is all the witness values must be elements in this prime field mod P. And in the SNARK that we are using, this KZG based SNARK, the P is like 254 bits. While in the ring polynomial, we can range from a modulus that can be up to 881 bits according to the standard. And this is already a big challenge because, okay, how can we even represent this without overflowing our prime P? And the solution, as you might expect, is leveraging this CRT decomposition. And instead of working with CT0, we work with its I, which is I CRT decomposition. So just to give you an example, we can, if we take like the larger Q according to the standard, which might be 881 bits, we can leverage 15 decomposition of the ciphertext by setting QI as 59 bits. And so in this way, we can safely represent the coefficients in our prime field of the circuit, and we can also perform operation on this coefficient without worrying about the risk of like potential overflow. So as long as we stick to the operation that are defined in the encryption, we have not this risk. And so we kind of solve the problem of representation, but now it comes to performing operation on top of this polynomials. And the operation that we want to prove is this one, the one that we defined before. And you notice that the the issue here is this modulo operation. So it's not something that is impossible. Well, we can also perform this modulo reduction inside our zk-SNARK, but it's just very inefficient. So to perform this operation inside the SNARK. So in order to overcome this issue, we kind of modify a bit the definition of our ciphertext polynomial by introducing two auxiliary polynomials. So we are somehow embedding these two auxiliary polynomials that are R2 and R1 inside the polynomial definition to replace the need to perform this modular reduction. And here you see how we go from basically we replace this reduction by this expression, and we replace this reduction by this expression. And what we get at the end, what is like the achievement here is that we can express this relation in ZP in the prime field of our SNARK without having to worry about further reduction and without having to worry about risk of overflow. So we get eventually, after some like moving stuff from the left to the right, to this expression at the bottom. That is what we really need to prove inside our SNARK. And just as a way to visualize things in a easier way, we can also rewrite this operation, this very last equality, by using this vector notation. And why we do that? I think this is needed to separate two vectors, u and s. And the important thing to visualize here is that all the vector of all the polynomials and the scalars that belong to this vector are public. So making them public is okay. We actually want to make them public. And of course, the ciphertext, the result should be made public to the verifier. What we want to hide are all the polynomials inside this S vector, because revealing them to the public will somehow break the security of the ring learning with error. So, of course, it will allow someone to retrieve the message, to understand your secret. So everything here should be private. Everything else is okay to exposing them to the public. And actually, it's not okay. It's required to expose them to the public. Another challenge that we have is to perform a large degree polynomial multiplication. So we defined before the polynomial ring, but we never really said how big is this ring, how big is the n at the exponent of the denominator polynomial. Well, it is like a power of 2, but like you can think of it ranging from 1024 to like increasing power of 2. So these are like very large polynomials, and since the operation are all like multiplication between polynomial, we need to find, this is like the biggest cost center of our circuit, and we need to find ways to make it efficient. And as a starting point, what we implemented was a very naive way of performing polynomial multiplication using the direct method, which is like, how they teach you doing like polynomial multiplication at school. And this was as like a quadratic complexity in n, which is the degree of this of these polynomials. But we actually implemented a trick to allow this to be done in a more efficient way. And this trick is based on the Schwarz-Zippel lemma, which basically says that if you want to check that this relation is true, so for example, that f times g equals to h, which are like three polynomials, you don't need to check this relation for the polynomial form, but you can sample a random point gamma, evaluate each polynomial at this random point gamma, and check that the quality holds true when the polynomial are evaluated at gamma. And this makes things much faster because we now get like to a linear complexity. So it's like O n, where n is the degree of the polynomial. And I think, yeah, this is the correct slide. So we kind of modify the constraint. So rather than having to enforce this constraint when all the polynomials are expressed in their large extended form, we can enforce this constraint when everything is evaluated at gamma. And the challenge here that you might wonder how is like, okay, how do we achieve, how can we draw randomness inside a circuit? And the answer is here. The technique basically proceeds as follows. We separate the proof generation into two phases. And in the first phase, we fill the witness with our secret polynomials of the vector Si. And we commit to the witness so far. We hash this commitment and extract. So you can think about like a polynomial commitment like KZG, but it's not really specific to any commitment, this technique, and we hash the commitment to generate this challenge gamma. And now we can use this challenge gamma in the second phase of the proof generation as randomness. So in the second phase, we're gonna, okay, of course, prove that the coefficient of these polynomials in SI are in an expected range. And then we evaluate everything at gamma based on this expression, and we prove that this relation holds. And what's the key here? The key here is that all the polynomials, the secret polynomial must be filled in the witness table during phase one, because this is how Fiat Shamir works, like as soon as a malicious prover is kind of aware of the challenge, they can think, oh, okay, now I can modify my polynomial such that the relation is true, even if it's not actually true. But as soon as they modify the polynomial, which are these secret polynomials, the challenge will change as well. So it's a kind of a spiral, and this is how we guarantee the security in fetching the challenge inside the zk-SNARK. And these are the benchmark of Greco. So you see, like I think the most notable thing is the proof generation time, and this is chosen across different security parameters according to the standard. The benchmarks are run on an M2 chip, and the implementation has been done using Halo2lib, which is a library developed by Axiom, and it works on a Plonk zk-SNARK that uses KZG commitments, and an extra component that I really didn't mention up to now is the SNARK, so like the succinctness of this proof. So you can see that the proof verification is really fast, and it also translates to a very small size of this proof that can be verified on chain potentially. And I also want to mention something like the K here indicates the number of ciphertexts. And what we are doing now is that we are not processing this ciphertext. So so 15 basically means that there are like 15 CRT decomposition of the ciphertext in the ring RQ. But what we are doing now is we're not leveraging any possible parallelization across these 15 components. So I think that this number, especially for a large case, can be improved by leveraging some parallelization and then aggregating recursively the proof into a single proof if you really want to put everything together. And there are also some sections that I omitted from the presentation for the sake of time. And this is like how you can calculate this auxiliary polynomial that I completely glossed over. Well, this one that I just mentioned, like the strategies of how you can prove the correct formation of many ciphertexts, you can either do this sequentially in a single proof or in parallel. How you can expand this secret key encryption to public key encryption. And lastly, how we can compose a Greco zk-SNARK with some application-specific logic. So this, going back to the example of the voting application, would be how we can compose it with your requirement for your application. And this section are all present in the paper. So going back to my original goals for this presentation. I will kind of synthesize the takeaways. So the main takeaway, I think, really is that almost any application will require something like this. And if you want to try your luck with Greco, it will be a good idea, I guess. But I also encourage like people to improve upon Greco because I think this is something really necessary for if we really want to see application being deployed in a FHE application being deployed in production. And lastly, about like the strategies, I think this can be synthesized in this three very simple steps. So we had the issue of how to represent this coefficient in a zk-SNARK. We solved that using a Chinese remainder theorem. Then we wanted to perform this ring polynomial reduction efficiently inside the circuit. So we leveraged these auxiliary polynomials that can be computed outside the circuit. Maybe I forgot mentioning that, but this is really important. They can be pre-computed outside the circuit and fed into the witness generation. And lastly, one of the biggest cost center was this polynomial multiplication, and we kind of solved that. We kind of made it more efficient using this challenge-based approach, leveraging two phases of proof generation and Piaget-Shamir heuristic. Again, yeah, related to what I was mentioning before, I wish there were like more improvements and on that, and the improvement can come from different directions, like using faster decay protocols, so the underlying protocol to be faster. For example, like people at Summa have been implementing this zk bootstrapping using Stark, which is probably faster than the, the proving protocol that I'm using. Or also, there's a team in a PSC that is now focusing on lattice-based SNARK, which I don't know, might probably yield a more efficient result. And as I mentioned before, leverage parallelization. And also on a more like engineering level, on a higher level, there's also possibility to improve the way the BFE algorithm is parsed inside the SNARK. So using tricks such as the one we employed for efficient polynomial multiplication. And lastly, there's also room for support other encodings and other FHE schemes. And I know that some people are interested in adding compatibility with like FHE, and there's someone that is now working on that. So we hope to have a further support soon. And we also are really open to contribution from the community. And this is the link to the GitHub implementation, which will then also contain the link for the paper itself. And yeah, I'm happy to take any question of any kind that you might have.